the next natural question to ask from a calculus perspective is if you can find the slope of a tangent line, it'd be nice to find areas, and specifically areas bounded by the curve. Polar coordinates, we think of rotating and then walking out. So we think of kind of this like a rotating fashion. We don't usually we don't walk left and right then up and down. So like rectangles don't really make a whole lot of sense in this rotation world. But you can still, we can still find areas in some sense. And we can find areas like between two angles of rotation, call it say alpha and beta. And we can try to find the area that's enclosed while sweeping out this angle around this curve. So we're going to use a similar process to that of the Riemann integral, but we're not going to use rectangles as the thing to subdivide. But we still can do a same limit process, just without a rectangle. And what I mean by that is if I'm kind of rotating around, it makes sense that I'm gonna like this is kind of like a circular sort of thing. So like maybe instead of estimating by like small rectangles, maybe I'll do like slivers or like parts of circles. So maybe I'll come up with some sort of estimate in that fashion. So I'm going to try to divide this thing. I'm going to estimate the area of this by dividing it into parts of circles or sectors. So my strategy is divide into sectors instead of rectangles and of equal angle. So maybe it looks something like this. A picture might look something like this. How about I start with this radius that corresponds with alpha, and I rotate a little bit, and then I walk out, and I find this area. And then I find the value of the function at that angle, and now this time I rotate at that radius. And now I have another sliver. And this time I start on the function and I rotate a little bit, and so on. And I keep doing this process until I've got an estimate, until I've subdivided this into a bunch of little like circular wedges or sectors. And I hope it's kind of just like in the rectangles for area under a curve in rectangular coordinates, that that if we were to make finer and finer estimates, we'd eliminate these little gaps, and we'd get closer and closer to the exact area if we made the width or the amount we rotate smaller and smaller and just added more and more wedges. So recall that the area of a sector in radians is 1/2 the radius squared times the angle in radians. So if I want to estimate the area of this thing, I could do 1/2 times, since this function is describing the radius in terms of theta, I would just take the value of this function at some given radius. How about the kth radius, the kth angle? And you just square that. That'll be the radius squared. Then I multiply by this little chunk of angle, and maybe I'll call like one of these little slivers, how about delta theta? All right, since we'll make them all equal, I won't need the sub k. So then I can get an estimate if I just sum over every one of these little rectangles. So if there are n wedges, then I just do this process n times. And this will give me an approximation for this area. And if I want it dead equal, then I would think of this process, but think of the limit as I subdivide it into finer and finer and finer angles. So the area should be dead equal to this limit. Or this limit should recognize as the definition of an integral. And this would be the definite integral over this entire region. And note this is where alpha less than theta is less than beta. So from this definition, we can find a formula for the area enclosed in these polar coordinates. And the area, the exact area, is an integral from alpha to beta of 1/2 the function, the radius function r of theta squared times theta. Oh, not times theta. The delta theta becomes d theta. Excuse me. 1/2 r of theta squared times d theta. So let's apply this and let's see if we can come up with the area of one of these of a polar graph. So here's a pretty common one. Let's find the area of one petal of the rose curve given by 3 cosine 3 theta. It'll be nice to know what that looks like in the first place so we can have a better idea of what's going on here. So maybe I'll quickly graph that. I'll make a new document. Add a graphs page. I'm going to menu, graph entry edit, and enter a polar graph. Or on your 84, just make sure you're in the mode setting that your graph mode is set to polar, and then just go to y equals. And I'm going to do 3 cosine 3 theta. 3 cosine 3 theta. Make sure there's a multiplying sign there so my computers get mad. Graph it. And I want one of these petals. So one of these petals, it doesn't matter, there is symmetrical, so it doesn't really matter which petal I choose. So in light of that, I'm going to choose the one that's kind of centered here on the x-axis. It would be nice to know what the bounds of this integration should be. Where should I, what should I integrate between? I think that you could do this in a variety of ways. I'm going to think of the bounds as like what would the slope of a tangent line be in here that gives that would be kind of like the wedges dividing the sky up into sectors where like a point is moving around this curve. Another way to maybe think of that is like when is the point going to be back to the origin? Like what are some zeros of this function? What are the thetas that bring the point back, have a radius of 0? And I think that's when the thetas that make cosine of 3 theta equal to 0. Cosine is equal to 0 at pi over 2. So the first positive theta that does that is pi over 6. 3 times pi over 6 is pi over 2. That's definitely an upper bound. So I know an upper in fact that's going to correspond to the slope of the tangent line that comes this way. So I know one bound is going to be pi over 6, and by symmetry you can see that the first negative version of that is in fact negative pi over 6. That would be if you rotate backwards, because at 0 cosine is 1, so it's when theta is 0, we're definitely way out here. And as you work backwards, the first time it hits 0 is, by symmetry argument, negative pi over 6. And when the angle rotates between these two things, we'll get this first petal. Since this is symmetrical, you could go from maybe 0 to pi over 6 and then just double your answer. There are a lot of approaches you could try this, but I'm going to go from a full petal. I know that the area is 1/2 times r of theta squared d theta. R is this guy. R of theta is 3 cosine of 3 theta squared d theta. So we need to integrate this somehow. Let's do a little bit of simplifying. I pull a half out. This expression squared is 9 cosine squared of 3 theta. And then I'll pull the 9 out as well. So this is like 9/2 integral from minus pi over 6 to pi over 6 of cosine squared 3 theta. So the question is, how do we integrate this? It's a little tough. You could probably do this by using integration by parts somehow, splitting this to cosine and cosine. It's definitely, you can't use just direct substitution because the derivative of cosine sine, there are no sines in this. There is a maybe handier way to do this, is so you remember some trigonometry, that we can actually, there's something called a power reducing formula. If you don't remember the power reducing formula, which is perfectly fine, there is a link between cosine squared and cosine, and that is with the double angle formula. So recall one of the double angle formulas for cosine. Remember, cosine of 2 theta is equal to 2 cosine squared of theta minus 1. This allows us to link together cosine squared and cosine. So since I have cosine squared here, maybe I rearrange this formula to get cosine squared by itself, which would be add 1 and divide by 2. So cosine squared of theta is cosine of 2 theta plus 1 over 2. So firstly, if I put a 3 theta in, then I need double that angle in here. So note, this integral is really from negative pi over 6 to pi over 6. I could substitute out cosine squared to get a cosine to the first power, which I can integrate, but I have at the price of doubling the argument. Plus 1 over 2 d theta. So from here, we can integrate this. I'm going to factor out this 2 and get 9/4 integral cosine of 6 theta plus 1 d theta with my limits integration that I'll fill in later. Let's integrate this with respect to theta. This should be 9/4 times antiderivative of cosine of 6 theta is sine 6 theta over 6. Antiderivative of 1 with respect to theta is just theta. And this is from negative pi over 6 to pi over 6. Let's plug that stuff in. This is 9/4. Let's see, sine of 6 theta times pi over 6 is sine of a pi, which is 0. Minus sine of minus 6 times negative pi over 6, which is sine of negative pi, which is also 0. Plus pi over 6 minus negative pi over 6, which is 2 pi over 6 or 1 pi over 3. This is 9/4 times pi over 3, which is works out to be 3 pi over 4.